Hello and welcome to this lecture. We've been seeing a series of spectral theorems and we're going to conclude with the last of them, which is complex spectral theorem, the general complex spectral theorem, and the associated matrices, which are called normal matrices. Okay. So far we've seen two, the real spectral theorem and this Hermitian matrix spectral theorem, which was sort of a mix of real and complex. Now we'll move to the general complex world and see this normal matrices and the complex spectral theorem. Okay. Okay. So what is the setting here? The setting is, we've been asking that question, if you have an operator T from Cn to Cn, maybe it's diagonalizable, right? It has a matrix representation A. I'm asking this question, what if this operator T is orthonormally diagonalizable? It's diagonalizable, it has orthonormal set of, it's diagonalizable, it's okay, we understand that a little bit. What about orthonormal diagonalizability? It's a bit stronger, right? Much stronger. And let's say it's orthonormally diagonalizable with eigenvectors v1 to vn. Okay, this is given to us. Now, we are not going to assume the eigenvalues are real. Okay, the eigenvalues may be complex. Okay, so far we have seen the case where the operator itself was from Rn to Rn. And then we went to Cn, but then we imposed this condition that the eigenvalues have to be real. That gave you the Hermitian symmetry. Now, I'm going to relax that also. I'm going to say, I only care about orthonormal diagonalizability. I don't care about the eigenvalues. Eigenvalues can be anything. Okay, then can you say something? What can you say about the matrix A? What can you say about the operator T? That's the question we're going to ask. Let's look at what happens then. Okay, so we know just because it has an orthonormal eigenvectors, it doesn't matter whether lambda 1 is real or complex, this result is true. A equals SDS inverse is always true. And of course, I can write it out like this. This is also true. Okay. But now, if lambda 1, lambda 2 are not real, you can't reduce this to Hermitian symmetry. You can't get that, that doesn't work, okay, because what happens to A Hermitian? You have the lambda 1 bar, okay. See, if lambda 1 were real, then A Hermitian will become the same as A, okay. You can see why, right? So, you can, when you do Hermitian on this total thing, you have to do Hermitian on each of these guys. Hermitian on V1 Hermitian actually is the same as V1 Hermitian, okay. You have to do V1 Hermitian whole Hermitian, which is V1 times V1 Hermitian, okay. But then the lambda 1 will become lambda 1 bar and that kills you. Because you are assuming lambda is to be complex, this A Hermitian will not be the same as A, okay. But then is there any other easy property that you can observe between A and A Hermitian, okay. It's not very obvious, it may not be very easy for you to see, but then you have A and A Hermitian, maybe we should try to multiply the two of them, okay. So, you can multiply A and A Hermitian, and when you do that, you notice that the cross terms will vanish. Why? Because of the orthonormality property. All the cross terms will vanish, only the corresponding terms will multiply, and when you multiply, those become real, okay. So, notice how the corresponding terms become magnitude of lambda 1 square, magnitude of lambda 2 square, and they become real. Okay, so that's a very nice observation. Once you observe this, you will see that even if I do A Hermitian A, I get the same answer. Okay, if you do A Hermitian A, multiply A Hermitian on the left and A on the right, again you get the same expression. Okay, so the moment you have orthonormal diagonalizability, even if lambdas are complex, the only thing you seem to be getting is A is what's called a normal matrix. What's a normal matrix? Any matrix that satisfies A Hermitian equals A Hermitian A is called normal. Okay. So, this is also not too bad to verify. Okay. A equals A Hermitian is very easy to verify. Okay. A Hermitian equals A Hermitian A, you have to do a few multiplications, but you can verify. Okay. You can quite easily verify. So, this normal condition is not too difficult to verify. Okay, I hope I've convinced you. So, you see now that if an operator T represented by a matrix A with respect to some orthonormal basis is diagonalizable with an orthonormal set of eigenvectors, then it is normal. Okay, that's what we have seen. A Hermitian equals A Hermitian A. This is the definition for what's called a normal matrix. Okay, so that's okay. You might ask what's the converse, right? So, we are interested in the converse. Supposing I have a normal matrix, is it true that it has an orthonormal set of eigenvectors? Okay. So, that is a question we will answer, but before that, there is this confusing world of symmetric versus Hermitian versus normal. Let me give you a few examples which will maybe clear it up a little bit for you. Okay. We are going to stick to orthonormal basis. Remember, we will only consider orthonormal basis in these kind of discussions. Okay. A real symmetric matrix is Hermitian trivially, right? Because if A is real, A transpose is A Hermitian, so A equals A transpose is the same as A equals A Hermitian, okay. But complex symmetric matrix need not be Hermitian, okay. So that's an important thing to understand. So here is a matrix A which is 1I1, A equals A transpose, but it is not equal to A Hermitian, right? Because if you do Hermitian, you're going to get minus I here, and that's not the same as I. So this is true. So you should be a little bit careful about complex symmetric matrices, because even if they are symmetric, they may not be Hermitian. Any Hermitian matrix, right, is normal. Okay, one way it's true. Any Hermitian matrix is normal, because if A is A Hermitian, then A Hermitian equals A Hermitian, A equals A squared. Both of these are the same, right? So if a Hermitian matrix is normal, but the opposite is not true. Normal need not be symmetric or Hermitian. Okay, so here's a real example. Even complex also you can come up with example. Here is a very, very popular example, 2 by 2. AB minus BA is actually normal. You can multiply and check. It's a very simple multiplication. You can multiply A transpose with A transpose A. You'll see that both are the same, but this is not equal to A transpose, right? B and minus B are there. So here is another more complicated looking example, but this is actually a circulant example if you think about it for a while. Circulant matrices are normal. You can check very quickly that these are normal, but this is not symmetric, right? Both of these are not symmetric, okay? So normal does not mean Hermitian, normal does not mean symmetric, but symmetric means, real symmetric means normal, complex Hermitian means normal, okay? So that's also important to understand. A couple of things. A normal is an operator property and not a matrix property with respect to orthonormal basis. Okay, so that's also something important. With respect to an orthonormal basis, as long as you're sticking to orthonormal basis, normality is an operator property. It doesn't depend exactly on the basis which we are using. That's important to understand. And a matrix that is that represents an operator, if the matrix is Hermitian, then that operator is called self-adjoint. Because if A is equal to A Hermitian, T is equal to T star, the operator is its own adjoint, so it's called self-adjoint. Okay, so this is the terminology you may see. A self-adjoint operator is represented by a Hermitian matrix. T equals T star, which means A equals A Hermitian. Okay, a bunch of definition and concepts. Hope this is clear to you about symmetric versus Hermitian versus normal and what's a self-adjoint operator. Okay, so I think now we are ready to state the complex spectral theorem. So earlier we already saw that if an operator Cn to Cn has an orthonormal basis, then the matrix is normal. Okay, so that's a quick thing that we saw. The operator itself is normal, matrix is normal. Okay, so that's a definition that we saw. Now it turns out this is if and only if the opposite is also true. The converse, not the opposite, the converse is also true. Okay, an operator T from Cn to Cn is orthonormally diagonalizable if and only if it is represented by a normal matrix A. So if the matrix A is normal, A Hermitian is A Hermitian A, then the operator represents ends up having an orthonormally diagonalizable, it ends up being orthonormally diagonalizable. It has an orthonormal basis of eigenvectors. Okay, so this is very, very interesting. So matrix A is normal, we can't say anything, there's no easy symmetry condition, right? It's a bit complicated. Only thing is A Hermitian equals A Hermitian A. You have to go and verify it. Okay, so it's not so simple. It may have complex eigenvalues. Once it's complex, I can't order them. Okay, so I don't know. Maybe I can order them in terms of absolute value, but not in terms of themselves. And the orthonormal eigenvectors, they end up being something like this. Okay, so we will actually see a proof of this complex spectral theorem. So once you see a proof of this complex spectral theorem, most of the other theorems also fall in place, right? Because Hermitian is also normal, so it will have an orthonormal diagonalizability. All of those things work out, so I'm not going to go into those subtleties. The only proof we'll do is the proof for the complex spectral theorem. The real spectral theorem needs a few more arguments. We will not see it in this course, but I'll encourage to look it up if you see them somewhere. Okay, but with this one we will prove. We will prove in some reasonable detail. Okay, so here is the proof. We have already proved one direction. If T is represented by A, if T which is represented by A is orthonormally diagonalizable, then A is a normal matrix. We have seen that already. We just saw that derivation just a little while ago. We have seen this already. We have to prove the other direction. If A is a normal matrix, then we have to show that T is orthonormally diagonalizable. As in there is a orthonormal, the eigenvector basis of orthonormal eigenvector basis exists, or it's not orthonormally diagonalizable. That's what we have to show. Okay. We'll start with Schur's theorem, and Schur's theorem is a very, very important starting point here. Okay, what does it say? For any T, there exists an orthonormal basis with respect to which A is upper triangular. I can go to upper triangular. I don't know if I can go to diagonal or not, but I can go to upper triangular using Schur's theorem. Okay, that's a very easy place to start. So, without loss of generality, we can assume this matrix A is upper triangular. Okay, so I have a normal matrix A, I have to show that it is diagonalizable, but I can assume that the normal matrix A is upper triangular because I can go to this orthonormal basis with respect to which A is upper triangle. So, we will assume it is upper triangle. Now, here comes a very important fact. This is a claim, we will prove it soon enough. If you have an upper triangular matrix and if it is normal, then it turns out it is a diagonal matrix. Okay, so, this is a very clean and very interesting fact. If you have an upper triangular matrix, additionally that upper triangular matrix is normal, okay, it satisfies A Hermitian equals A Hermitian A, then it turns out all the off diagonal elements have to be 0, they cannot be non-zero. Just by that property you can check this, okay. So, we will prove it, it's quite easy to see and prove, but once you have this claim you are done, because I already know A is normal, right, and A is normal, and using Shor's theorem I can assume A is upper triangular. So, clearly that means A has to be diagonal, and which means there is an orthonormal basis with respect to which the operator T has a diagonal representation, it is orthonormally diagonalizable, and we are done. Okay. So, this is the simple argument for the proof. I have Shor's theorem which says I have triangular with respect to some orthonormal basis. Now, if I have normal and triangular, then I know it is diagonal, which means with respect to that same orthonormal basis, my operator becomes diagonal, which means it is orthonormally diagonalizable. Okay, so that's a very simple way to prove this complex spectral theorem. Seems simple enough. At the end of the day, there are a lot of pieces, but finally it's a very simple proof. Now, the only claim left to be proved is upper triangular matrix that is normal. Upper triangular and normal implies diagonal. Okay, so it's actually a very easy proof. We'll start with 2 by 2. Okay, as usual, 2 by 2. So, I'm going to start with an upper triangular matrix, okay, which is also normal, let's say A, B, 0, D, and maybe it's normal. So, what is A Hermitian? It's this guy. What is A times A Hermitian? It's this guy, right? So, you can multiply these two, you will get this expression. And what is A Hermitian A? You get this expression, right? So, just stare at these two elements, okay. So, if the 1, 1 element has to be equal, right, A Hermitian equals A Hermitian A, then B has to be 0, right? It's quite easy to see. So, A is diagonal. So, 2 by 2 it's very trivial, normal and upper triangular implies diagonal. You can also do 3 by 3 just to get our hands a little bit more dirty. You can try 3 by 3, you will look at 1, 1 entry of A Hermitian, okay, no need to worry about all the entries, okay, 1, 1 entry of A Hermitian, you will see will be mod A square plus mod B square plus mod C square. You can see A times A Hermitian, the first entry will be mod A square plus mod B square plus mod C square, right. Hermitian first column is the first row transpose conjugate. So, when you multiply you will get this. What about 1, 1 entry of A Hermitian A? If you do A Hermitian A, you will get A bar 0 0 in the first row. So, it will only be mod A squared. So, if these two have to be equal, notice these two are non-negative, right. So, if these two have to be equal, then B has to be equal to C has to be equal to 0. So, first row we have shown already that BC has to be 0. So, you have to show all the off diagonal elements are 0. So, one by one I can show everything works out and B comma C has to be 0. Now, I am left with this form for A. I have this E here, and again I will look at 2, 2 entry. If you look at the 2, 2 entry of A Hermitian, you will get mod D square plus mod E square. 2, 2 entry of A Hermitian A is simply mod D square. So, from there you get E equals 0 and A ends up being diagonal. Okay, so, this is another way in which you can see for 3, 3, and now you see what to do, right. The general case, you just proceed as above. You start with the 1, 1 entry, the first row or everything off diagonal will go to 0. Then go to 2, 2 entry, in second row all the off diagonals will go to 0, 3, 3, 4, 4 till n minus 1, n minus 1. So, all the off diagonal elements are 0 and you get A to be diagonal. Okay. So, upper triangular and normal implies diagonal is a very powerful idea in showing that normal matrices are orthonormally diagonalizable. Okay. So, that is the proof of the complex spectral theorem. Let us see an example. Always examples are good to see. Here is an example 1, 2, minus 2, 1. I know this is normal, it is not symmetric. Okay, eigenvalues are going to end up being complex. The eigenvectors are also complex in this case. This particular case is real, but nevertheless you have a picture like this. And then we have our spectral decomposition result, right, the spectral theorem, which is the general form for a 2 by 2 normal matrix. Lambda 1 and lambda 2 can be complex now. That is what we are seeing here. And if you plug it in, you are going to get an expression like that, and you can see this 1, 2, 2, 1 is actually written as sum of this matrix plus this matrix. You can multiply and check, and that works out. It's just a spectral decomposition for the matrix A. okay, and powers are very, very easy. It's just lambda 1 squared, and then a power k also is very, very easy, right? So the orthonormality property continues to hold. So all these cross terms will go off to 0, only the corresponding terms will be there. The lambda I are complex, but nevertheless you can raise them to the power and do the computation. So for normal matrices, powers are very, very easy because of that relationship. Okay. So let me summarize all the diagonalizability spectral theorem results that we have seen so far. I will quickly summarize. We start with an operator T, Cn to Cn. It's represented by a matrix A with respect to some orthonormal basis. Adjoint is T star. It's going to be represented by A Hermitian, right? So that's the starting point. Let's say T is diagonalizable. If it is diagonalizable, the only thing I can say is Cn has a basis V1 to Vn of eigenvectors of T. Okay. Now I can still write this relationship, except A equals SD S inverse. Now the rows of S inverse cannot be easily written in terms of V1. I mean, of course you can write, but it will be a very, very complicated sort of expression. It won't be very simple, okay, because these V1 to Vn are only linearly independent. They are just a basis. Now my T is only diagonalizable. I can't say anything connecting W1 to V. But nevertheless, I can use my multiplication property and I can write like this. Except powers are a little bit not that complicated, because we do have some properties. Powers are easy in this, but nevertheless I think it's not as easy as it could be, right? So I think this property is important to know also. Even for diagonalizable you have this, but from here we can't go to any simple property of A. It's not like A equals A transpose, A equals A Hermitian, A Hermitian. You won't get any simple property like that, because this is very, very generic, okay. So this is also, but anyway, nevertheless for diagonalizable you have a structure like this, right? So but this W and V are not arbitrary. They are related to each other by inverse, okay. So this is all you can say if you only insist on diagonalizability. But once you go to orthonormally diagonalizable, if you know that Cn has an orthonormal basis of eigenvectors of T, you can say so much more. Once you have that, you see that S and then S inverse becomes Hermitian. Once it becomes Hermitian, you know that it has very, very simple properties. So you start with any orthonormal basis, you write like this, plug in your lambda, your favorite lambdas you like, complex, real, whatever, you get a orthonormally diagonalizable matrix A. Okay. So that's very important. Now we also know that this form has a very simple relationship. A Hermitian equals A Hermitian A. Very easy to check. In general, these things may not be true, but for the orthonormal case, this becomes very, very easy to check. Okay. So that's the first spectral theorem result that we had, the complex spectral theorem without any further assumptions. Lambda 1s could be complex, anything, whatever you like. This is the most general fact that T star equals T star T. T is normal if there is an orthonormal set of eigenvectors. Okay. So next thing, we specialized it a little bit. We said if the lambdas are real, okay, I'm still in Cn, I'm still in the complex world, but if in addition the lambdas are real, then you can say more. If the lambdas are real, then the operator becomes self-adjoint. A becomes equal to A Hermitian. Okay. So if it's complex, you can't say this, but if lambdas are real, then you end up being A equals A Hermitian. All these are, you know, if and only if. The other way also is true. If A equals A Hermitian, it has real eigenvalues and has an orthonormal basis of eigenvectors. All of these are true. Okay. And finally, the result that we saw is the self-adjoint case, where you specialize to Rn. You say T is Rn to Rn, everything is real, lambda is real, V is real. In that case, A becomes a symmetric matrix. Okay, so A equals A transpose, because the Hermitian doesn't really apply. So you have A equals A transpose. Okay, so this sort of summarizes all the diagonalizability and spectral theorems that we saw so far. Okay, thank you very much.